Hello, hello. So I was just watching a video on car crashes the other day, the ones with the test dummies, and I thought, well, what is the physics behind this? And now I'm going to explain to you what forces act on us and the car when we crash and what we do to mitigate the damage by taking advantage of the physics in the crash. All right, now let's start with momentum. Momentum measures how much motion something has or the quantity of motion something has. You calculate it by multiplying mass and velocity. Now, one main thing about mass is it should not be confused with weight, where weight has the factor of gravity on it. Where, let's say you're on Earth, you would have the gravity on Earth affecting how much you weigh. Obviously, it does include mass, but it changes from planet to planet, unlike mass, which stays constant on any planet that you are on. And velocity can just be said as speed. So let's take two cars. Car A, which weighs 1500 kilograms and is moving at 20 meters per second, and car B, which is 1200 kilograms and moving at 15 meters per second in the opposite direction. Since they're going in the opposite directions, car A's momentum can be taken as positive and car B's momentum can be taken as negative. To find the total momentum, we would just add them together. And here, the law of conservation of mass states that momentum doesn't just disappear. Whatever the momentum is, has to be the same after the collision, and the momentum stays constant even if the cars crumple or bounce off of each other. And this is why momentum is so useful in car crashes, because it helps us figure out how motion was distributed between the cars after they collided. Now, let's talk about energy, specifically one of two types of energy: potential energy, which is the energy held by an object before it's put into motion, and kinetic energy, which we're going to be talking about right now, which measures the energy of an object during motion or because it's moving. Here's the formula. The formula for kinetic energy is 1 by 2 mass into velocity squared. Now, the formula for momentum, as we calculated, was just mass into velocity. Now, kinetic energy is a big deal in collisions because it tells us how much energy was involved in the crash. Unlike momentum, kinetic energy doesn't stay the same during a collision. Some of it gets converted into heat, sound, and damage into the cars. Now, for example, if the cars start with 100,000 joules of energy and end with 70,000, that means 30% of the energy was lost. This loss translates directly into how much damage was done to the cars. This is where safety features like crumple zones come in. They're designed to absorb kinetic energy as much as possible during a crash, protecting passengers by controlling how much energy is distributed. These features save lives. All right, now that we've understood why and how momentum and kinetic energy apply to car crashes and how they help us save a person from a car crash, we can model it now in Python and see if the person actually survives the car crash or not. We've taken the mass of the car, the velocity of the car, and the mass of the person. Here we've just taken an estimate for how much momentum would be fatal to a person. So we've taken 250 kilogram meters per second for fatal momentum, and then like an extreme fatality rate for kinetic energy would be like 10,000 joules, and then like a high fatality rate would be like around 5,000 joules. Then we take the initial momentum, which is the mass of the car, into the velocity of the car as we calculated, and then we take the velocity as zero, the final velocity, and then we take the final momentum at the mass of the car and the final velocity of the car, which we've taken as zero. Then we have to actually calculate the change in momentum, as we can't really take it as the initial momentum because that's not what happens to the car. So we have to actually take the change in momentum for when the car's moving and when the cars crash. And we take the initial momentum, subtract it from the final momentum. Then we have to actually calculate the initial kinetic energy, which is zero point 0.5, or instead we could just say 1 by 2 into the mass of the car into velocity square, as we learned. Then we have to take the final kinetic energy as well, which we would just do the same because kinetic energy formula always stay the same. Same thing with momentum, by the way, it doesn't change. We've just taken the velocity for this as final velocity for this as zero. Same thing here. Final velocity is zero. Now we calculate the change in kinetic energy, which is the initial kinetic energy subtracted from the final kinetic energy, and this is the energy lost in the crash. Now, we actually get to the part where it determines if it is fatal or not. We check if the momentum risk is fatal, and if we see that if the change in momentum, delta p, is higher than the fatal momentum, which we taken as 250, and if it is, then it directly says, okay, this is a fatal impact. Or else we say the momentum is within survivable limits. Then after that, we actually calculate the kinetic energy. So we say if the change in kinetic energy is higher than the extreme kinetic energy, which we took as, 100,000 joules, then we would say that it's definitely fatal. It's extremely fatal. Or else, let's say the kinetic energy is lower than extreme fatal kinetic energy, but higher than high fatal kinetic energy, which is 5,000, it's within that range, 5,000, 10,000 joules. Then we'd say, it's high fatal, highly fatal, but not extremely fatal. Then finally, we would check maybe, okay, so they've not taken that much impact, not 5,000 joules, maybe like under 10, 5,000 joules within like 1,000 joules. Then we'd say, okay, if the kinetic energy, change in kinetic energy is around that range, then we'd say, okay, serious injury, but not completely fatal. Or else we'd just say, okay, this is survival impact. Then we just print all of this, and now let's actually test this out. Let's take the mass for car A from our previous example. So let's say, 1500 in kilograms, and then the impact, as we said, was 20 meters per second. And then let's say the person's mass, let's take an average mass, like around, let's say, 70 kilograms. All right, now the initial momentum is 30,000 kilograms meters per second, and the momentum change is 30,000 kilograms meters per second because we calculate the final velocity as zero, and zero into any number would be zero, so it's just 30,000 minus zero. Then we'd say the momentum risk assessment here is the impact is fatal and the momentum is high. And then now we calculate the initial kinetic energy, which is 300,000 joules, and the change in kinetic energy is 300,000 joules as well, as we calculated, because velocity is zero, so it's just 300,000 minus zero. And we'd say this is extremely fatal. So in the end, the person dies, unfortunately. Hope you've learned why and how kinetic energy and momentum are helpful in our daily lives, and you've learned why they're useful in car crashes. That's pretty much it for today. Thank you so much for watching, and if you did enjoy this video, I'd like for you to drop a subscribe, and that's pretty much it. See ya!